Hello everyone, welcome to our third lecture in fluid mechanics. In this episode we shall be covering velocity vector fields. A velocity vector field is a vector function that defines the velocity of your particle as it moves through the flow. If you plot enough of these particles, you will get the velocity profile of your entire flow. Well, how do we find the velocity vector field of a flow? Well, first we have to know what the position of the particle is with respect to time. That is what R of t here notes. R of t is the path of the fluid particle as it moves through space. As moves through space. And if you remember from kinematics and physics, the velocity is equal to the derivative with respect to time of the position. This applies to vectors. So, reviews now the velocity profile. Well, the velocity profile will change with time, of course, but it can also change with position. Your x-coordinate, y-coordinate, and z-coordinate can all affect how your velocity profile looks. Therefore, your velocity profile, even though r is a function of time, your velocity profile is a function of x, y, z, and time. And of course, if you recall, you can break up a vector into I hat, j hat, and k hat for the x, y, and z direction respectively. Well, here in fluid mechanics, this is how you do it. We represent the I hat direction with u, x, y, z, t, I hat. J hat is going to be in v, x, y, z, t, j hat. The z direction will be omega, or w, x, y, z, t. So this would be your entire velocity vector field as represented in this, where u would be your velocity in the x direction, v would be the velocity in the y direction, or omega would be the velocity in the k direction. And as you can all see, these are all dependent upon x, y, z, and t, which is x-coordinate, y-coordinate, zeta-coordinate, and time. So this function itself is very useful for dictating what types of flows you're going to have. But just the velocity profile itself it's useful, but it's not going to be used just as its own. What you're going to be using it is to define your parameters of your problem that you're going to be dealing with, as well as use it in other base equations. But right now for this video, we're going to use it to define our flow itself. Well, if you recall in my earlier videos, especially the Bernoulli's derivation, one of my parameters was steady state, or the flow is steady. Well, what does that mean? Well, a steady flow means that the velocity does not change with time. So partial v, partial t is equal to 0. This is the best case scenario because when you're doing all your other functions, which I'll show you later on in this video for your streamline, streak line, and path lines, you have to take derivatives. And if it's steady state or steady flow, it removes one of the derivatives, makes your problems a lot simpler. Well, guess what? If you have steady flow, you have the opportunity to have unsteady flow. Unsteady flow just means the velocity does change with time. And that problem makes your life a lot more difficult. Trust me. Just imagine it. You're having to deal with an extra derivative in whatever you're solving. It's going to be more difficult. So a lot of the time you're going to be dealing with a steady flow assumption, and it's going to make your life easier, and you can use the steady flow analysis to approximate a lot of the flows you're going to come across in real life. And also, this is an introductory course. Later on, not in this course specifically, but in the next couple years or so, we'll be going over more advanced engineering topics, and in those episodes, we're going to have to come across unsteady flow. But for this course, we're just going to always assume steady flow. So this is it right now for velocity vector fields. This is the basics. Well, now we're going to cover the next topic, which would be streamlines, streak lines, and path lines. So this is our next topic, streamlines, streak lines, and path lines. Well, when do you use streamlines? Streamlines are when you're analytical, you're just doing the math of it. So, well, this entire course, we're going to be concerned about streamlines because we're doing the mathematical approach to flows. Streaklines and path lines are used more in experimental. When you have a setup or some sort of apparatus, you have a flow going through it. At that point, when you're doing everything experimentally, you would use streaklines and path lines, which I will define later on in this episode. But for right now, we're going to cover streamlines, which is the analytical or mathematical approach to fluid analysis. So let's do streamlines. Do not remember changing color, but I'm sure that's somewhere in the video. Well, what is a streamline? So let's say I'm going to do 2D. Make my life easy. We're just explaining a concept. We don't need to go full out. So what is a streamline? Well, a streamline is a line that is tangent to your velocity vector at all points. So if I have a plot here and I have some velocity field, at this point here is my tangent. I'll change it to a different color. I'll go blue. This here is my tangent vector. So this would be my streamline. Well, in a 2D shape, I'm going to have my dx direction and my dy change. Well, also in 2D, you can have your velocity in the u and your velocity in the y, because this angle, theta, is shared by both triangles. Oh, this is supposed to be v, not y. Because this angle is shared by both triangles, because I'm just doing slope, rise over run. So if these two are equal, then dy, or if this theta is shared by these two triangles, then dy over dx must equal v over u. This equation here, this relationship, is how you're going to solve all your streamline problems and how you're going to find them. Because recall, v and u, remember, not dealing with z, v and u here represent the x component and the y component of the velocity field vector. So if you know those, you can solve this differential equation here, and you can create the equation for your streamlines. Well, how would you do that? The best way to show it is with an example. So let's do an example. Change back to black. So I have my velocity vector field here, v naught over L times negative x in the I direction plus y in the j direction. Okay, well, remember, v is ui plus vj. Remember 2D, so we don't care about what w is. Well, what is u? U is equal to negative v naught over L x. What is v? V is equal to v naught over L y. Well, now that I know what my u is, and I know what my v is, I can substitute here in my streamline equation, and I can calculate the equation of my streamline. So, let's plug it in. I get dy dx is equal to v over u, which is equal to v naught y over L over negative v naught x over L. This is going to equal to negative y over x. All right, so my equation for my streamline differential equation is this. Well, I have to solve this. I can't just leave it as is. I need some sort of function that defines it. This is 2D, so I need a 2D function. Well, to solve that, I have to do separation by variables. So dy over negative y is equal to dx over x, or you know what, I'm going to make this positive, this negative, because I want to. So let's integrate this. We're going to get ln of y is going to plus c1 is equal to negative ln of x plus c2. Isolate them over. Ln of y plus ln of x is equal to c3, because that'd be c2 minus c1. I can just call that c3. Combine the logarithms. This becomes ln of xy equals c3. Exponentiate it. I get xy is equal to some constant. So this equation here defines my streamline for the flow for this velocity vector field, all by using the equation that the slope here is equal to the same slope at a different point if I went some velocity horizontal and the same velocity vertical. So this is now my equation for that streamline. Well, what does that look? Let's plot it. Now, I would, if I could, I would share Desmos and I would show you all different plots, but I can't right now, but I also plotted it earlier, so I can just show you. So, y, x, this is what your flow is going to look like. If c equals 0, you're going to get this type of flow. So imagine those are straight. If c equals 1, you're going to get this type of flow. C equals 2, that type of flow just gets bigger and bigger. If c is negative 1, if c is negative 2. So here you go. This defines what your streamline will look like depending on what your constant is. Of course, your constant depends on the different types of parameters you have, or I'm sorry, not parameters, initial conditions you would have for your base velocity equation and your base differential equation. I did not have any. I'm just showing you an example of how to find the streamline of velocity vector field and the importance of a streamline and what a streamline is mathematically and actually. So I'm not going to have the initial conditions. I'm just doing the general formula of it. And of course, as always, if you have any questions, I highly encourage you to leave a comment and I will answer it as soon as I can. I'm pretty good about it. I mean, no one's left questions, but I'm also very good. I check to see if I have comments and I'll of course answer them as soon as I can. So this covers a streamline. Now let's cover what a streak line is, and we shall change color for that to black again. So a streak line. So, if any of you have a car or glass or whatever, and you've noticed watermarks on it, like a path that a droplet might go, say on your car if it rains, or in a window if it rains, what that is called a streak line. That is what it's leaving behind. That is a lab, and it's used in lab tool instead of analytically to determine the paths of certain droplets. So, how would you do this? Well, you do it by tracking certain particles in a flow. Particles in a flow. Now, sometimes they'll use dye. For example, if you have some sort of, let's say I have some sort of flow going like this through my container, they'll inject a dye here, and this dye will follow the flow particles throughout. That red line here would be a streak line. And if you've noticed, like you have a car window seal here, and you have like a droplet going down that's left some sort of path behind it, that path here on your window would be a streak line. That's why those on your glass are called streaks. So, fun fact there for you. There's a mathematical reason behind it. So, up here, now if the flow is steady, that means that the velocity is not changing with time, it's just changing with position. Your streak line will be constant. It will not change as the experiment goes on because the velocity vector field is not changing with respect to time. It's just changing with respect to position. Therefore, your streak line will only change with respect to the position of the particles. So you'll just have one particle flowing after another predictably here, and your streak line will therefore be constant. Now, if your flow is unsteady, that means it is changing with time as well as space, which means, say, I have here point 1 and here point 2, and I let a second pass, and this is unsteady flow. Well, my velocity here at point 1 will not be the same as my velocity here at point 2, based regardless of steady or unsteady, but now my velocity here at point 1 is not the same as the velocity at point 1 a couple seconds ago and a couple seconds from now. Therefore, my streak lines will change with the velocity flow, and they will no longer be constant. This you start getting with, for example, in turbulent flows, your streak lines won't be constant, but in developing or unsteady flows, your streak lines will also not be constant. So, last thing we have to do is a path line. Well, what is a path line? Well, it's exactly what it is. It's the path the particles take during the flow. Path of particle during the flow. Now, there's a sprinkler example in the book, or my book, that I could have shown you and done the calculus for, but it's a very long problem. The point of that problem is this, though. So I have some sprinkler, right? And this sprinkler is moving back and forth. Well, if I'm analyzing the entire flow, when it's going, you're gonna get a flow that looks like this, right? Going from the sprinkler's head, because as it moves back and forth, one droplet shoots up here, then another droplet shoots up here, and so on and so forth as it's moving back and forth. No droplet is put from the same spot. Therefore, my streamline, which I shall show in blue, would end up being like this. There's a mathematical analysis for it. Again, it's very long, and a majority of this video's runtime would just be the analysis. If you're interested in it, I'd recommend looking up vibrating sprinkler problem, and it'll cover that, or we can cover it in another video. If you guys want me to cover it, I'll cover it in another video. Well, the blue would be the streamlines. That's the fluid velocity field as the sprinkler's moving back and forth. Well, path line is the physical path a particle takes. Well, when I shoot up a droplet, let's change colors to black. If I shoot up a droplet here, that droplet is going straight. This droplet here is going straight. And then what causes this streamline is there's a particle shot up here, 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 and all those particles are going straight upwards, which are path lines. But since each particle is being launched from a different position, it forms that type of wave that you see. So if you ever had a hose and you vibrate it back and forth and you get this like squiggly pattern like this, try that. Have a water bottle hose and vibrate it back and forth as it's going. You're going to get this type of path in your water. That's what it's going to look like. But it looks like that because each water droplet is being launched from a different x coordinate here. All these particles were launched from a different x coordinate. But each particle will only go straight. It's just since they were launched in this pattern of line here will go forward at like that, and those particles will have that same position, creating your streamline. But your path line is what the path the particle physically takes. So that is a streamline, a streak line, and a path line. Well, there's mathematical equations for that, which you usually don't cover. I mean, no, you do cover it, but you really don't go in depth on it. At least my professor didn't. I don't know about yours. But if you want me to go into more depth on the math behind it, leave a comment. I will make another video specifically for going into the math of the path line, streak line, and streamline more. Well, the last topic we're going to cover tonight is going to be an acceleration field of the flow. Acceleration field. And it's going to be for inflows. It's going to be for steady and unsteady flows. Now you might be thinking, but wait, John, isn't acceleration the rate which speed changes with time? Yes, but remember, acceleration is just the change in velocity, but it can also, if a velocity changes direction, if you remember from Newton's laws, a body in motion will maintain its motion unless acted on by an outside force. Well, that outside force the velocity change had to have been caused by a force, and since the droplets have mass, therefore they had an acceleration. Therefore, you can have acceleration with a change in distance, or change in direction, I'm sorry, not change in distance, change in direction, and a change in time. So, let's do that. So, I am sorry. Here we go. Let's continue. Sorry about that. So remember, I have my velocity vector field here of r of t, and for simplicity's sake, let's make it x of t, y of t, z of t. So it's still going to change with each direction. X, y, z, and t all change. And we're going to make it where x can change as a function of time, because remember we took a derivative of the vector field. Well, we took a derivative of it in the x direction as it changes with respect to time, the y direction as it changes with respect to time, and the z direction as it changes with respect to time, and time as it changes with respect to time. So let's write out the vector. So a hat, or not a hat, just the vector a, is equal to dv dt, which is equal to, remember this is full derivative, partial derivative of v with respect to t, plus partial derivative of v with respect to x, partial x with respect to t, plus partial v with respect to y, partial y with respect to t, have to use the chain rule, plus partial v with respect to z, partial z with respect to t. Now, you might have recalled earlier I said u is the velocity of the particles in the x direction, v is the velocity of the particles in the y direction, and w is the velocity of the particles in the z direction. Well, dx dt, change in position, change in time, that's u. dy dt, that's v. dz dt, that's w. So, my vector equation here becomes dv dt, I'm sorry, it used to be partial derivative, dv dt plus u dv dx plus v dv dy, different v, this is the velocity vector, should all be vectored, plus omega dv partial v with respect to z. Now I want to break it down further into my components. Well, I need more space here. So if you want to jump ahead a minute, want to make more space real quick, actually never mind, my space is made. Alright, so what's the velocity, or the acceleration vector in the x direction? Well, partial u, partial t, because remember, v is u, v, omega, plus u, partial x, plus v, partial y. Now these are the same v. I'm sorry, that's not the same v. That's my mistake. I made that. It's not. This is partial u, partial x, plus v, partial u, partial y, plus omega, partial u, partial z. A in the y direction, partial v, partial t, plus u, partial v, partial x, plus v, partial y, plus omega, partial v, partial z. Now, this v and this v are the same v. They're the speeds of the vector that results in the speed in the y direction, all right, or the velocity in the y direction. So a sub z, and I'm guessing you already wrote it out, it's omega this time. Same thing, just omega. There you go. This would be the acceleration field of, or the acceleration vector field of the flow. So now let's do an equation. Let's do an example of it. Let's solve it. So I have my velocity profile here where V is equal to, it's incompressible and inviscid. So incompressible, inviscid. And I want V will be a function of U, X, I, plus V, Y, J. So I'm saying these are one-dimensional. U only changes in X. V only dependent upon Y. Z will only be or omega will only be dependent upon Z. So I just made these one-dimensional. And this function is going to equal 1 over x squared I. And I want to say it's steady state. Well, what does this mean? Well, inviscid and incompressible just means that if the faster you go, the fluid is not going to compress itself because then the equations change, which we will cover in this series, not right now, but in this series, compressible and incompressible fluid. Inviscid just means that the shear forces between the fluid is not really, actually I forgot inviscid. I'm pretty sure that means I'm not going to say because I'm going to be honest, I forgot right now. I would have to look it up. I did not write about it in my notes. And steady state means that it's not changing with time. So, well, if I have no j direction and no k, which means u is equal to 1 over x squared, v is equal to 0, omega is equal to 0, well, that means ay is equal to 0 and az is equal to 0, because that's derivative of 0, 0, 0, 0, 0 for a and z. Ax, though, is not the case. So ax is equal to partial u, partial t, plus u, partial x, plus v, partial u, partial y, plus omega, partial u, partial z. So, well, there's not changing with respect to y, so 0, 0, and also v and w are also 0, 0, so 0 times 0, 0. Steady state, not changing with time, so a of x is u, partial x. Need a little bit more space. So let's do that. That's going to be a sub x is going to equal 1 over x squared times, well, that's going to be negative 2 over x cubed, which is going to equal to negative 2 over x to the fifth. Therefore, my a vector is equal to negative 2 over x to the fifth I. And that would be my vector acceleration vector equation there. So let's do, this was a long video, so let's recap all the way back up here at the top. If you have a particle, R of t denotes the path of a particle as it moves through space. You're dealing with fluid, so it's going to be a fluid particle, like a water droplet, for example. If I take the derivative of the path of the particle with respect to time, I get the velocity vector field of the particle. And if I take enough I've got the velocity vector function. If I get enough particles, I have a vector field. So, and that is denoted with my equation here, where u is a function of all four coordinates, x, y, z, including time, and that denotes my velocity vector in the x direction, v is the y direction, omega is the z direction. Steady state means that the velocity does not change with respect to time, so dv dt is 0. If it's unsteady, that means it does change with time. Problem gets a lot more complicated. Your velocity field will change with respect to time. Then, once this was covered, we went to cover streamlines, streak lines, and path lines. Streamlines are tangent to the velocity vector field at all points, and you can represent it here with this streamline equation here, where you can see that the angle for the two triangles here is the same, which would be the slope of the streamline. You can represent it here with dy over dx equals b over u. We then did a mathematical example, which if you want to go in depth of how to solve it, just rewind it whenever the time is that we cover this part. Plotted out vector function. Streak lines is the lab you're now experimental, and you're actively physically tracking those parts. Like, so if you have a flow, you're injecting some sort of dye, you're watching a water droplet move down a screen or a film, whatever. Steady and unsteady. If it's steady, the streak line will be constant as it changes with time and will only change with respect to position because particles will move one after another and they will follow the same path. If it's unsteady, velocity changes with respect to time. The particles will be fluctuating each time, so your streamline will not be steady. It will change as the fluid changes. Path line is the physical path of the particle. So if you shoot a particle, doesn't matter what the sprinkler is doing, doesn't matter what anything else is happening. The particle is just going to simply move straight or parabolic motion, depending how you're doing it. So if you were to vibrate a hose back and forth, like this is your hose up here and you're vibrating it back and forth like this, well, each particle is still going to go strictly straight. That is the path line. The streamline would be how the particles are all flowing together. Again, if you want me to do the math, request it. I'll do the separate video of that. The reason I didn't cover it is you don't really deal with it in this course. It's not really covered in the book. Acceleration field and flows, just taking the derivative of the velocity vector field. We're going to do the full derivative, so you have to do a series of partials and the chain rule, like this. You notice that, well, dx dt is the velocity in the x direction. Well, represented earlier, that's u. Velocity in the y direction is v, lowercase v. Velocity in the z direction is omega. So plug those in and you get your velocity vector field equation. And here you can break it down into the individual ax, ay, and az components. And here we do an example with the derivative and everything of it. And again, if you want the math, I'll be happy to go back in and do it. Well, I already did the math. If you want more examples of it, just leave a comment and I will get back to you. In the description, I will define what inviscid and compressible is, as I did not define it here in this video. Thank you very much, and I hope you have a wonderful evening.